What is its nature? Basic in nature. What type of base it is? As it is NH3 grade, it is an example of fluid base. When dissolved in water, it produces ammonium hydroxide, which dissociates to the. So, in aqueous medium, it can be taken as an example of argineous base. But in terms of strength, it comes in the weak base category. Further, the basic character of ammonia can be identified by means of its chemical reactions. When ammonia is made to react with mineral acids like HCl, H2SO4, H3PO4, you will get corresponding salts. With HCl, you will get ammonium chloride. With sulfuric acid, you will get ammonium sulfate. With phosphoric acid, you will get ammonium phosphate. All these compounds are commonly used as nitrogenous fertilizers. Right. So from all these examples, we can say that nature of ammonia is basic. Right. Next, how it reacts with halogens. Next problem. Reaction with halogens. So depending on the experimental conditions, different products are possible. If ammonia is meant to react with the excess of chlorine, the products are mixture of nitrogen trichloride and HCl. But if excess of ammonia is made to react with chlorine, products will be mixture of ammonium chloride and nitrogen. Right. Here, quantity of ammonia is changing, quantity of chlorine is same. But in the statement, how we write ammonia reacts with excess of chlorine, excess of ammonia reacts with chlorine. But fact is, quantity of chlorine is same in both the cases. What is changing? Only quantity of ammonia is changing. Right. Next, oxidation. So oxidation products also keep on changing. When ammonia is oxidized directly in the presence of platinum as catalyst, you will get mixture of nitric oxide and water. Same reactants, but no catalyst, and products will be mixture of nitrogen and water. And in both the cases, ammonia is undergoing oxidation. Right. Next, reaction with the transition metal ions. Reaction with transition metal ions. All the transition metal ions, most of the time, are associated with characteristic colors. So, what is the color associated with cupric ion? Lower bluish green. The color what we observe, that is called as complementary color. Why? A transition metal ion or transition metal shows color. Why? A 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 tran absorption of energy in the visible part of the radiation. Whichever part is absorbed, opposite will be emitted. And whatever is emitted is called as complementary color. How to identify the complementary color? There is a scientific method. Like this, violet, violet, blue, green, yellow, orange, red. In the picture, which part is missing? Indigo is missing. Except indigo, all other colors are present. So when violet is absorbed, complementary color what you observe is just opposite color we have to choose. If red is absorbed, complementary color will be either blue or green. If you get minus, you take it. That's a red light. Resultant color either blue or bluish. So like this, we can identify colors of the complex ions. So further, for the confirmation of transition metal ions, we can make use of the reaction with ammonia. Here, even though we say reaction with ammonia, actual reaction will be taken with ammonium hydroxide. So when ammonia is dissolved in water, first you will get ammonium hydroxide, which dissociates to the NH4 and OH minus ions. So if this is the general notation of transition metal ion, depending on the charge, it will take so many OH minus ions and you will get corresponding metallic hydroxide. And these metallic hydroxides will be insoluble. They are observed in the form of precipitate. And they will carry the color of the transition metal ion. So from the color of the precipitate, almost we can identify what is that transition metal ion. Say for example, cupric ion you take. How many OH minus ions it will take up? What is the charge present on it? Plus 2, so 2 OH minus. What do you get? Cupric hydroxide. So in order to take up 2 OH minus ions, how many ammonia molecules must dissolve? Again, equal to the charge. So this cupric hydroxide form, it will be a blue colored precipitate. So if you get blue colored precipitate on the addition of ammonium hydroxide to salt solution, conversely, what is the statement? The salt consists of cupric ions. And if you add excess of ammonia, what happens? This precipitate gets dissolved due to formation of a soluble complex. How do you name that complex? Already coordination compounds are completed. What is the name of this complex? Complex, is it in the form of cation or anion? Cation. So when it is in the form of cation, from where you will begin? Coordination number. What is the coordination number? 4. 4 is called as tetra. What is the lineage present here? Ammonia is called as amine. Then transition metal atom, copper. In bracket, you have to write the oxidation state in Roman numbers. External part is hydroxide. In this, copper oxidation state is plus. So you write like that. And the color of this complex compound is deep blue or dark blue. So why the precipitate is soluble means due to formation of this soluble complex. Similarly, if you take silver ion, it will take a 1 OH minus ion and it's converted to silver hydroxide. is the color of silver hydroxide? Silver is having bright, shining color. But what about silver hydroxide? It is almost dull. It slowly turns to black color. So formation of such kind of display indicates the presence of silver ions. Here also, this silver hydroxide is again soluble in excess of ammonia. So those complexes we have to remember. Silver hydroxide dissolves in excess of ammonia and gives this soluble complex. It is called diamine silver hydroxide. Right. Similarly, zinc ions, they will take a 2 moles of OH minus ions and initially they form zinc hydroxide. What is the color of zinc hydroxide? It will appear as a white gelatinous precipitate. And just like the previous cations, it is also soluble in excess of ammonia. And the soluble complex formed here is ZnH3 taken 4 times OH plus. So initially we get white gelatinous precipitate which dissolves on the addition of excess of ammonia. Similarly, if Fe plus 2 ions are present, they will pick up 2 moles of hydroxide ions and you will get FeOH twice ferrous hydroxide. And what is the color of ferrous hydroxide? Same as the color of ferrous ion. What is the color of ferrous ion? Pale green color. But unlike zinc, silver, or copper, this is insoluble in excess of ammonia. So only precipitate is formed and that will be retained. Suppose Fe plus 3 ions are present. They will take a and product form is FeOH taken plus. What is the color of ferric hydroxide? Brown color. And ferrous ion is easily oxidized to ferric ion. So when you are doing test for ferrous ion, initially you will get pale green color precipitate. But within seconds what happens? Its color turns to brown due to conversion of the ferrous ion into ferric ion. Similarly, suppose Mn plus 2 ion is present. It will take a 2 moles of OH minus ion and gets converted into MnOH plus. What is the color associated with minus hydroxide? Pale green. So like this, from the color of the precipitate formed, conversely, we can identify what is that transition metal or metal ion. So all these reactions are used in qualitative analysis for the identification of cations. So in that way, ammonia acts as a very good laboratory reagent. Right. So that is about the reaction with the transition metal atoms or metal ions. Right. Then what is the use of this ammonia? 90% of ammonia is used for the production of urea. And urea as it is used as fertilizer. Then ammonia is used in the manufacturing of nitric acid also. That we will see later. And ammonium nitrate, which can be used as a fertilizer as well as an explosive also. Mixture of aluminium powder and ammonium nitrate, it is called as ammonal. These combinations you have to remember. And ammonal is used in the making of what? Landmines. Landmines are used for what purpose? They are a type of explosives, right? So mixture of aluminum powder and ammonium nitrate, it is called as ammonia and is used as powerful explosive. So all these things come under the category of uses of ammonia. Right. Next, and the last compound in this topic. Nitric acid. So how to prepare it? What are its properties and uses? So preparation methods, we study under two headings: laboratory methods and industrial methods. In the laboratory, nitric acid is prepared by the action of sulfuric acid on any nitrate salt. So nitrate salt means either we can take NaO3, then it will become sodium nitrate. In place of Na, you can take potassium. It will become potassium nitrate. Calcium also you can take, then it will become calcium nitrate. So when any nitrate salt is heated with sulfuric acid, concentrated sulfuric acid, exchange of ions will take place. So if you are using sodium nitrate, products will be sodium sulfate and nitric acid. And the sodium sulfate, so often it is known as salt cake, right? If you are using potassium nitrate, you will get potassium sulfate and nitric acid. If calcium nitrate is used, products will be calcium sulfate and nitric acid. So like this, by the action of concentrated sulfuric acid on any nitrate salt, nitric acid can be prepared in limited quantities. That's why these are all called as laboratory methods of preparation. Next, industrial methods. Industrial methods. Here we will come across two methods. One is called phosphorus process and another one with clamp and heights process. Right. So take first method, phosphorus process. In this phosphorus process, starting material is ammonia. Ammonia is subjected to oxidation in the presence of platinum as catalyst. So we will get nitric oxide and water as liquids. These equations are not balanced, you have to balance them. Then the nitric oxide octane is oxidized to get nitrogen dioxide. In the next stage, that nitrogen dioxide is dissolved in water to get nitric acid. Side product will be nitric acid. So this nitric oxide can be recycled to the second stage. So what is the role of nitric oxide in this method? Is it one of the reactant or shall we consider it as catalyst? Catalyst. Initially it is participating in the reaction, but at the end it is coming out unchanged. So in the second and third stages, which is actually participating in the reaction, nitric oxide is getting regenerated. So only nitrogen dioxide is getting converted into nitric acid. So these three stages taken together we call it as Oswald's process. Then Birkeland and Eid's process. It is also similar to Oswald's process. Only the first stage will be different. Instead of taking ammonia, here air is subjected to electrical discharge. Electrical discharge means passing high voltage current. What happens? Both combine together to get nitric oxide. Remaining stages are common. That nitric oxide is subjected to oxidation to get nitrogen dioxide, and nitrogen dioxide on dissolving in water will produce nitric acid. So between the two methods, which is a better method? Oswald's method or this Birkeland and Eid's method? In Oswald's method, starting material is ammonia, which is not a natural product. It has to be produced by some other method. Here, cyanamide already has to be. Moreover, you have to make use of what? Costly catalysts. Whereas here, it is A, which is free of dust. Any catalyst is involved? No. That way, this method is economical compared to Oswald's method. And in both the methods, the concentration of nitric acid produced is same. It doesn't make any difference. So, the nitric acid produced by either Oswald's process or Birkeland-Eid's process is initially dilute. So, its concentration has to be increased. How can you increase the concentration? Just you have to remove the water. How can you remove water? Nitric acid is liquid. Water is also liquid, but they differ in their boiling point values. So by means of fractional distillation, components can be separated. And by means of fractional distillation, concentration of nitric acid can be increased up to 68%. At this particular composition, the 30% nitric acid means what is the quantity of water left out? 32. At this particular composition, you will get a geotropic mixture, or what we call a constant boiling mixture. So some compositions we have to remember, like alcohol, water, at what composition they form a geotropic mixture? Roughly 96%, 4%. Similarly, when it comes to nitric acid, it is 68-32. So remaining water you cannot remove by means of fractional distillation. So the remaining water is removed by heating with concentrated sulfuric acid. Then concentration of nitric acid increases up to 98%. Still, how much of water is left out? The 2% cannot be removed even by sulfuric acid also. So as it is, that 98% concentrated nitric acid can be used. But if you are specific, it should be 100%. Then it should be cooled with this combination, ether and dry ice. Dry ice is nothing but solid carbon dioxide. When this 98% concentrated nitric acid is cooled with this mixture called as freezing mixture, then remaining 2% of water is also remove, and you will get 100% pure nitric acid. So that is regarding concentration of nitric acid. Right. Then, what are the properties of this nitric acid? This nitric acid comes under a strong oxidizing acid category. And the type of reaction, it depends on the concentration of nitric acid and the nature of the reactant as well as the temperature. Particularly, when reaction is taking place with metal, if dilute nitric acid is used, the product will be either nitrous oxide or nitric oxide. If concentrated nitric acid is used, then product will be nitrogen dioxide. In addition to these gaseous products, corresponding metallic nitrate will be obtained. So that is reaction of nitric acid with metals. Instead of metals, if you make use of non-metals, the non-metals will be oxidized to their highest oxyacids. Highest oxyacid means non-metal will carry the highest possible oxidation state. Say for example, you take iodine. What is the highest possible oxidation state for iodine? Iodine belongs to which group? 7th year group. So for any element, highest oxidation state is equal to its group number, so plus 7. So when iodine is treated with nitric acid, you will get what? This acid called as, what do you call this acid? Iodic acid. And iodine oxidation state will be how much? Plus 7. Suppose you take carbon, it will be oxidized to its highest oxyacid. What is the highest oxyacid for carbon? The carbon, what is the highest possible oxidation state? Plus 4. So what is the corresponding acid? What do you call it? Carbonic acid. But carbonic acid, is it stable or unstable? Unstable. So readily dissociates to get water and carbon dioxide. So when carbon is made to react with nitric acid, final products obtained will be mixture of water and carbon dioxide. Similarly, if you take sulfur, when nitric acid is made to react with sulfur, what is the highest oxyacid that we can expect? For sulfur, what is the highest possible oxidation state? Plus 6. In which acid that plus 6 is observed. So sulfur will be oxidized to sulfuric acid on reaction with nitric acid. That will say after both with metals as well as non-metals. And if you take base metals like iron, aluminium, chromium, when these are treated with nitric acid, what happens? Initial reaction takes place. But because of that initial reaction, what happens? A layer of oxide will be formed on the surface of these metals. And that thin layer of oxide will act as a protective reagent for remaining metal. So, what is called passivity is attained when these metals are made to react with nitric acid. So that particular reaction is used for practical application. By treating these metals with nitric acid, we are able to protect them from corrosion, isn't it? If these metals are exposed to air, what will happen? That corrosion can be prevented by making these metals to react with nitric acid. What is the protective agent found on the surfaces? Nothing but its oxide. So if iron is taken, iron oxide forms Al. Aluminium oxide will form Al. If chromium is taken, chromium oxide layer will be formed. Like that, these metals can be protected by treating with nitric acid. Right? So that is about properties. In addition to these normal properties, special reactions you have to remember. Like how this nitric acid reacts with glycerin or glycerol. What is glycerin? This trihydric alcohol is called as glycerin or glycerol. So when it is going to react with nitric acid, what do you get? For our convenience, nitric acid, you can imagine that is HONO2. So what happens? Like this elimination of water takes place. And these hydrogen atoms are replaced with NO2 groups. And what do you call the resultant product? Starting compound is glycerin. So product will be called as trinitroglycerin or trinitroglycerol. Commercially, it is known as what? Dynamite. What is the use of dynamite? Explosive. Who discovered it? Who discovered dynamite? Nobel Prize. What is Nobel Prize? Alfred Nobel was the scientist. He discovered this compound and he used it to manufacture and sell it. And his nickname was Merchant of Death. Because dynamite ultimately what is its purpose? So he was called as Merchant of Death. So what he has done? Whatever money has accumulated by selling this dynamite, he kept it as a deposit under his name only. And from the interest, even today, scientists are given the prize, what we call Nobel Prize. So if somebody is receiving Nobel Prize means he is receiving it from what? This bloody compound dynamite. Right? So in the examination point of view, what is dynamite? What is its chemical name? That you have to know. What is dynamite? Similarly, when cellulose is treated with nitric acid, you will get what is cellulose? One of the polymer of glucose, carbohydrate. The OH groups of cellulose will interact with nitric acid, and resultant product will be called as nitrocellulose. This nitrocellulose is also known as what? Gunpowder. So again, as the name is indicating, what is its use? Explosive. Now it is related with guns, but it is also used as an explosive, just like that. Then one more familiar reaction that you know, what do you call? Tolling. So when this tolling is subjected to nitration, you will get this compound. What do you call? Trinitrotoluene. So again, what is its use? So you can say 90% of nitric acid is used for the production of what? These explosive compounds. Remaining 10% of nitric acid is used in the manufacturing of fertilizers. Right? Then one more important aspect what you have to remember is mixture of concentrated nitric acid and concentrated HCl is called as alpha region. What is the composition? Nitric acid 1 mole, 3 moles HCl, 1:3 molar ratio. And what is the specific application of alpha is here? It can dissolve noble metals. How many noble metals are there? Only two. What are they? Gold, platinum. So when gold and platinum are made to react with alpha is here, how they get dissolved? First, gold or platinum will be converted into corresponding chlorides, and those chlorides are converted into corresponding acids. With gold, you will get this acid, HAuCl4. This is called as orochloric acid. Similarly, with platinum, you will get HPtCl4. It is called as platinic acid. And these are soluble in water. But by the decomposition of those compounds, again you can get back the metal salts. Right? So that is aqueous. So these are applications of nitric acid. And one more historical application that you have to remember here is Holmes signals. In Holmes signals, what is the composition used means calcium carbide and calcium phosphide mixture. So in olden days, when GPS was not developed, these signals were used for navigation of ships during night time. What is the chemistry involved? When this mixture is thrown into water, what happens? Calcium carbide undergoes hydrolysis to produce estrogen. Calcium phosphide undergoes hydrolysis to produce phosphate. And this mixture instantaneously catches fire. So, in the water, you can observe what? Flames. So, during night time, flames are observed means behind the flames, ship is coming. So, that kind of signaling is called as Holmes signals. But it is purely historical in nature. Now, nobody is running ships based on this kind of signaling system. What is the signaling system used now? GPS. Right? So only for chemistry people we have that purely historical. Right? So that is about the various compounds of 58 group elements. In addition to this regular content, you have to remember the structures of oxy acids of phosphorus. Phosphorus gives number of oxy acids, and these are classified under three heads. Lower oxy acids are called as S series of phosphorus acids. Higher members are called as X series. And a peroxy bond is also present in the acid. That series is called as peroxo series. So all these structures I have mentioned in the material. What is common thing among all these oxy acids is phosphorus atom will be sp3 hydrogen state. Water will be type of oxy acid. So when sp3 is the hybridization, what is the resultant structure? Tetrahedral structure. In each compound, you have to check for number of OH groups. And OH group will release H plus ions. So what is the basicity of an acid means? You have to check for what number of OH groups. Best example in a series, first acid is H3PO3. As per the formula, we expect its basicity to be 3. But practically, what is its basicity? Only 2. Why? Because if you refer to the structure, you can see 2 hydrogens are present in OH form. Only they undergo ionization to produce H plus. Right? So like that, once you check the sequence. Important aspect, what you have to remember is what is the oxidation state of each phosphorus. How many lone pairs are present, how many sigma bonds, how many pi bonds. This kind of data they are asking. Right? So for that purpose, compulsorily you should recollect, remember the structure. Right? So that is about one particular group, that is the fifth A group elements. Okay. Under the similar lines, you have to study the remaining groups also. Next to the fifth group is sixth A group, also called as oxygen family. According to IUPAC convention, it is named as 16th group. And based on the nature of elements, this group is known as charcoal family. What is meant by charcoal? Or gen means produce. These elements, they are mostly associated with what? Ores. Particularly, what are the various elements present? Oxygen, sulfur, selenium, tellurium, polonium. The first two members, if you take, they are associated with the number of ores. So, for example, it can be ores of iron. What are the various ores of iron available? One is oxide form, Fe2O3. This one is what? Hematite. Another ore is Fe3O4. We call it as magnetite. Another ore is FeS. We call it as iron pyrites. Like that, you take any ore. 90% of the ores come under the category of either oxides or sulfates. Very few come under the category of chlorides, nitrates, carbonates, and sulfates. So, as the first two elements are closely associated with number of ores, based on these two elements, this family is known as chalcogen family. Right? So that is general introduction regarding the 68 elements. Then rest of the things as usual. First we have to see the general physical properties, then general chemical properties, and followed by important compounds of this group elements. Right? Take this already. General physical properties. What is the first general physical property? Electronic configuration. What's the general configuration? NS2, NP4. N58 plus NS2, NP3. Now it will become NS2, NP4. How the atomic numbers change? What is the sequence order? 8, 1, 8, 183. So oxygen atomic number, if it is taken as 8, sulfur atomic number will become 16. Selenium will become 16 plus 18, 34. Tellurium will become 34 plus 18, 52. 52 plus 32, that will be the atomic number of polonium. Then easily you can write down the configurations of individual groups. Oxygen, helium followed by 2s2, 2p4. Sulfur, neon followed by 3s2, 3p4. Argon followed by 3d10, 4s2, 4p4. Krypton followed by 4d10, 5s2, 5p4. Xenon followed by 4f14, 5d10, 6s2, 6p4. So whatever analysis we have discussed in fifth theory of elements, same thing is applicable here also. Only outermost configuration is similar. Number of electrons present in the inner shells, they are different. And oxygen completely differs from the rest of the elements. Reason, configuration. It cannot expand the configuration due to non-availability of vacant d orbitals. Again, sulfur is different. It can expand its configuration. Chemistry of selenium and tellurium will be somewhat similar. Polonium, again, entirely different because of this difference in configuration. Right? Then what is the next property? Physical state and metallic character. So these things are there just to test your memory power. How good is your memory? What is the physical state of oxygen? Gas. Rest of the elements exist in solid state. What about metallic character? Oxygen, sulfur, both are non-metals. Selenium, tellurium, both come under semi-metals or metalloids. Polonium is a radioactive metal. So overall, what is happening to non-metallic character? Decreasing. Metallic character is increasing. So this trend is same as with the yellow elements. Right? Next. What is the next property? What is the next property? Atomicity, molecular structure. How oxygen is present in nature? In two forms, it is O2, O3. O2 form is called as, we commonly call it as oxygen, but chemical name is dioxygen. O3 is known as ozone. So in O2 form, what is the atomicity? 2. What is the molecular structure? Linear. Right? In O3 form, what is the atomicity? 3. What is the structure? Angular. And there is no clarity regarding position of these bonds. So you draw one more structure. It is a resonant hybrid. Overall structure can be called as angular. And the resonating hybrid can be represented like this. That's why oxygen bond length is equal in both the bonds. So this structure is correct. This structure or this structure? None is correct. Suppose this is correct, one should be having double bond correct. Double bond is always shorter than single bond. But practically observed thing is both are having equal bond length. Why equal bond length means ozone exists as a resonance hybrid of these two canonical forms. So overall structure of ozone will be called as angular. That is regarding oxygen. What about sulfur? In how many different forms sulfur is available in nature? In allotropy also same thing will be repeated. Alpha form is there, beta form is there, gamma form, delta form, epsilon form. Both alpha and beta have got SH. Gamma and delta have got SN. Epsilon has a SX. So in alpha and beta form, what is the atomicity? 8. Alpha form is called as rhombic sulfur. Beta form is called as monoclinic sulfur. And what is the structure of SH? It's a familiar structure called as round shape or puckered ring shape. Puckered ring shape. We draw the structure like this. Okay. What is the covalency of sulfur in SH? Covalency means how many covalent bonds is there on the average. Here one sulfur, here one sulfur. Like that, total how many sulfur atoms are there? 8. But on the average, each sulfur is involved in how many bonds? 2 bonds. So covalency of sulfur in SH is how much? 2. Right? What about the remaining 2 bonds? That is called polymeric form. Because number of sulfur atoms are connected with each other. And the shape will be like that. What do you call this shape? The teeth of saw. What is saw? The teeth, they will look like this. So here also what is the covalency of sulfur? 2. Right? In epsilon form, there are 2 possibilities. One is called chain structure, another one is called boat structure. How chain looks like? Assume that this is the chain. At each corner, one sulfur atom is present. So how many sulfur atoms are there? Right. So what is the covalency of sulfur in chain form? Again 2 only. What about boat form? Twist this chain like that. Then it will become boat form. Right. So again, what is the covalency of sulfur? 2. So these things can be taken as allotropic forms also. So under the same heading, atomicity, molecular structure, we are discussing allotropic forms also. Right? What about selenium and tellurium? Being semi-metals. Semi-metal means what? It will have both metallic character as well as non-metallic character. So those forms themselves are called as allotropic forms. Metallic form is gray in color, non-metallic form is blank, and they are supposed to exist as tetraatomic molecules. Last one is radioactive metal, and a little bit of history is also associated with this metal. This scientist is related with polonium. One of the lady scientists is associated. And because of this element only, concept of radioactivity came into picture. Madam Curie. And without knowing the consequences, she has conducted experiments. And as a result, what happened? She died at a young age of blood cancer. So thereafter, nobody dared to touch the radioactive elements. That's why our knowledge about radioactive elements is almost zero. Just like x tends to zero. Mathematically, x tends to zero means what? Not exactly equal to zero, but almost equal to zero. So that's why we don't know much about the characteristics of radioactive elements. So it will not be included in any of the convention. Right? So that is atomicity, molecular structure, as well as element. These structures carefully try to look, particularly sulfur. Right. Next. What is the next physical property? So here itself we can compare one more property also, catenation. What do you mean by catenation? Self-linkage of atoms. So which element has got the maximum catenation capacity here? Sulfur, you can see. Right? What is the highest catenation? 8 means limited number only. SN form is there, no? Gamma and delta. What is the formula we have mentioned? SN. Right? Among all the elements, which has the highest catenation level? Carbon. Next to carbon comes sulfur. Next to sulfur comes phosphorus. Okay? So catenation capacity in this particular group is maximum for sulfur. The rest of the elements, the catenation is almost negligible. Say you take oxygen. How many oxygen atoms are connected with each other? On the average, 2 only. Ozone you take. One oxygen is connected with how many other oxygens? Directly. Only one. Even though formula we write as N4, average number of parts produced is 1. What about polonium? We don't know much. That is the correct answer. Right. Next. What is the next property of comparison? Just to check out the list. Same headings get repeated. Oxidation states. What is the common oxidation state of oxygen? -2. Under special conditions, oxygen can show -1. Where you will get -1? Peroxides. In superoxides, it will be -1/2. In monofluorides, it shows +1. In difluorides, it shows +2. So total oxygen can show how many different values? 5 values. But range is in between -2 to +2. Higher values are not possible. Why they are not possible? Because oxygen has no vacant p orbitals. It cannot expand its configuration. But when it comes to sulfur, selenium, and tellurium, they can expand their configuration. So, in addition to common oxidation state -2, these three elements right. Sulfur, selenium, and tellurium, they can show how many different oxidation states besides -2. They can show +2, +4, as well as +6. Right? Regarding polonium, if we come to know about its properties, which is suitable oxidation state, it is metal. Generally, down the group, the highest oxidation state value decreases. So you may get these two. Right? So tendency to show negative oxidation state value decreases down the group. And one more analogy is what is the group number? Sixth group. According to IUPAC convention, 16th group. Even number or odd number? Even number. Look at the oxidation state values. They are also even. If you check the 50A group elements, 50A or 15th number is odd number. What are the oxidation state concerns of 50 group elements? -3, +3, +5. What are they? Again, odd numbers. Right? So that is about the oxidation state values. Remaining properties will continue. And from your side, are you practicing or not?